The last type of operators remaining are the bitwise operators. There are different bitwise operators as you can see on the screen. They are used with binary numbers. So, using these bitwise operators, we can perform multiple operations on binary numbers. Binary numbers, if you recollect, are the numbers that belong to the binary number system. If we use bitwise operators with non-binary numbers, those numbers are first converted to binary number system. Then, bitwise operations are performed. Finally, the result obtained is converted to decimal system and displayed. Let's learn about them now. First comes bitwise AND. This is its truth table. The notation for bitwise AND is exactly the same as logical AND. We write one AND symbol. Its working is also the same as logical AND. Only difference is, instead of true and false, we write 1 and 0 respectively. 1 is same as true, and 0 is like false. Here's a shortcut to remember this table. Bitwise AND evaluates to 1 if both the bits are 1. For any other combination, it gives 0. Next is bitwise OR operator. This is its truth table. It is represented as a one-pipe symbol. Not just that, it also works exactly like logical OR operator. Here's a shortcut to remember this table. Bitwise OR evaluates to 1 if any bit is 1. It gives 0 only if all bits are 0. Next comes bitwise XOR operator. Again, same notation as logical XOR. Working off bitwise XOR is exactly the same as logical XOR. As seen from this table, XOR evaluates to 1 if the two bits are different. If both are the same, it gives 0. The notation for bitwise NOT is different from logical NOT. Logical NOT uses the exclamation symbol, whereas the symbol of bitwise NOT is called tilde. As you can see from this table, NOT inverts the bit value. Thus, if bit A is 1, NOT of bit A is 0. Next comes the bitwise left shift operator. It is expressed using two less than symbols. It's very simple. All it does is shift all the bits to the left. Let's evaluate the expression 8 left shift 1. 8 left shift 1 means shift each bit of 8 to the left by 1 place. So, first we'll have to convert 8 into the binary number system. 8 in binary is 1, 0, 0, 0. Then, shift each bit to the left by 1. So, 1, 0, 0, 0 shifted to the left by 1 place will look like this, right? Notice there is an empty space created because of this shift. So, internally, a 0 will be added in this empty place, as you can see on the screen. Thus, we get 1, 0, 0, 0, 0 in binary, which will be converted to decimal system, and the output is 16. Now, what if the question said left shift 8 by 2 places or 3 places? It's not feasible to every time convert the number to binary, then left shift and do all that stuff. The good news is we have a shortcut. Here it is. Each left shift operator multiplies the number by powers of 2. So, if the question is A left shift by n places, the direct answer is A multiplied by 2 raised to n. Applying this rule for the same question, we get 8 into 2 raised to 1, which is 8 into 2 equals 16. We've got the direct answer. Easy, right? Let's move on to the next operator. We have the bitwise right shift operator. Right shift is represented by two greater than symbols, followed by the number of places to shift to the right. It's similar to the previous case. We just shift to the right instead of left. For example, we have this question. It means right shift 8 by 1 place. The steps remain the same as we did for left shift operator. So converting 8 to binary gives 1, 0, 0, 0. Then shift each bit to the right by 1. When we right shift 1, 0, 0, 0 by 1, the last bit will be eliminated. Hence, we get 1, 0, 0. So the answer we get is 1, 0, 0 in binary, which will be converted to decimal internally, and the answer is 4. Pretty easy, but it's complicated to do so many steps when there's an easy way out. We have a shortcut rule for right shift operator. Each right shift divides the number by powers of 2. So if the question is a right shift by n places, the direct answer is a divided by 2 raised to n. Applying this rule for the same question, we get 8 divided by 2 raised to 1, which is 8 by 2 equals 4. So we've covered all the bitwise operators. There are some more versions of bitwise operators that you can see highlighted on the screen. These are the compound versions of the bitwise operators. It works exactly the same as compound logical operators. For instance, if we use the and equal to operator, we say A and equal to B, which means perform A and with B and store the result in variable A. So it's similar for the rest of the operators, okay? We're ready to move on to some practice questions. See you in the next video.